Now that we've proven the chord theorem, let's take a look at a couple sample problems to see how easy it is to apply it to solving real-world problems involving the lengths of line segments and circles. So if we head over to the document camera, here are two past regions questions, and these are both in the short answer part. So this is in part 2. So in the accompanying diagram of circle O, chords AB and CF intersect at E. If EB, you know me, whenever I'm reading along and having numbers and I've got a diagram that doesn't have numbers in it, I'm going to copy the numbers in. That's just smart sense. If EB is equal to 16, AE is equal to 5, and CE is equal to 10, we want to find EF. All right, so the one I don't know, I'm going to call X. And all we need to do to turn this into a formula is that the two parts of one of the chords multiplied together, 5 times 16, is equal to the product of the two parts of the other circle, or the other chord, which is 10x. All right, and so now it's just a matter of doing some multiplication. So 5 times 16 is 80, is equal to 10x. We divide both sides by 10, and x is equal to 8. So that's all we need to do in order to solve the problem. Let's take a look at another problem, which is just a little bit tougher, but it's the kind of thing that the Regents throws at you every once in a while, and I will throw at you every once in a while. So once again, we've got a circle and we've got two chords intersecting, but this time, instead of giving us the lengths of the sides as numbers, we're getting expressions all in terms of x. So here AE is equal to x, EB is equal to x plus 1, CE is x minus 1, and ED is 2x. And now we need to find out what AE is, which is x. So basically we're just solving for x. So it looks like a harder problem, but really it's the same basic idea that we used in the first one. The two parts of this chord have lengths x and x plus 1, so we're going to multiply them together. And then we're going to multiply together the two segments of the other chord, which are 2x and x minus 1. And we could distribute here and we'd get some quadratic expressions, and that, that's something we could handle. We're not shy about things like that. But why don't I make life a little bit easier to myself, because I can see that both sides of the equation have a factor of x. And so I can just divide both sides of the equation by x. I know x isn't 0 because x is the length of this line segment, and that's definitely not equal to 0. So if I divide both sides by x, those are going to just vanish. And so now we've got a much easier job. On this side of the equation, we just have x plus 1. Over here, we will distribute, and that gives us 2x minus 2. And so to solve this for x, I'll subtract x from both sides, get all the x's over on one side. So we have 1 is equal to x minus 2. What minus 2 is equal to 1? You could solve it that way, if you know that, and of course you do. Or if we want to be in full algebra 1 mode, we'll just add 2 to both sides, and we get that 3 is equal to x. Let's double check our work by plugging those numbers back into the circle and seeing if it satisfies the chord theorem requirements. So x is equal to 3, so AE is 3. EB is x plus 1, which is going to be equal to 4. X minus 1 is equal to 2. And 2 times x, 2 times 3 is equal to 6. So does that satisfy the conditions of the chord theorem? Yeah, this side is 4 times 3, which is equal to 12. And these two segments multiplied together are 6 by 2, which is equal to 12. So we get 12 either way. And so that verifies our solution that AE is equal to 3. So that just gives you a couple basic ideas of how we can use the chord theorem and how it comes up in problems that we can solve for things that actually have a number as our answer.